video, we are going to be covering problem number 35 from chapter 27 of the Fundamentals of Physics, and I'll link the textbook in the description. So let's read the problem. In figure 27, the electromotive force is equal to 12 volts, R1 is 2000 ohms, R2 is 3000 ohms, and R3 is 4000 ohms. So we're asked to find what are the potential differences from various points, various junction points in our circuit. So we have VA to VB, VB to VC, VC to VD, and finally VA to VC. So, starting off, the first thing that we need to recognize is that this circuit is not easily condensed into a parallel or series circuit. So we can't solve this problem by finding equivalent resistances by rewriting the circuit into something simpler. So we're going to have to use a different approach. And this approach is called nodal analysis. So essentially what we're going to be doing is we're going to be analyzing the current at various junction points. We have A, B, C, and D. So in order to do this, we need to first designate one of our junction points as a reference junction or a reference node. And we're going to set that reference node to have a voltage of 0. Now the most logical choice for the reference node is definitely going to be VD, or sorry, the point is going to be D, and the voltage at that point we're going to set to 0. So why point D? So if we look at our circuit, we have our battery, and our electromotive force is going to be going in this direction. So it'll hit A first, so all 12 volts will be hitting A, junction point A, and then from there, the voltage will trickle down these different resistors and these different paths, and finally we'll get to point D, and at point D, this is the last junction point before it goes back to the negative terminal of the battery. So naturally, it makes sense to set the voltage, the reference node, to be D. So once we do that, we know that VA is going to be 12. And this is, as we mentioned, because our electromotive force is 12 volts, and the first junction point we hit is A. So naturally, A is receiving all 12 volts. Now what we need to find is what is VC and VB. And we can do this using our nodal analysis. So we're going to be analyzing the current flow through each of these resistors, and then from there we will be finding our VC and VB. So first off, we need to indicate the direction of the current that is flowing through each of the resistors. So if we follow our current, at point A, our current's going to split and go this way. And here it's a little tricky. We can say that our current flows in this direction or it flows in this direction. It's not really clear which one is the correct one, but for the purposes of the problem, I believe either direction for the current to flow through resistor 3 will result in the same answer. Let me know in the comments if anything changes if you flip the direction. And of course, our current will continue on down this way to get to point D. And then finally from D, it's going to be just flowing back. So this is our direction of current flow. Now, we're going to be using Kirchhoff's current law in order to do our analysis. So recalling our Kirchhoff current law, we can recall that Kirchhoff's current law states that the sum of the current into a node is equal to the sum of the current outside of the node. So let's perform this analysis on junction point C. So we can say that in junction point C, our current is going to be coming from R2, and current is found using this equation, so V equals IR. So what's our voltage through this resistor? Well, voltage always goes from higher potential to lower potential. So we're going to have current through resistor 2 is going to be VA minus VC, and we're going to divide by our resistance based on our Ohm's law. So VA minus VC divided by R2, and we also have current coming from resistor 3, coming through resistor C, so from this direction. So that's going to be VB minus VC over R3. And finally, this is the current in, and this is going to be equal to current out. And the current flowing out of the junction C is going to be through our R1. So that's going to be VC minus VD over R1. So now we can plug in values for our equation and see what we get. So we know that VA is equal to 12. So 12 minus VC over R2, which is 3000, and plus VB minus VC, both of these are unknowns, over 4000, and that's going to be equal to VC, which is unknown, minus 0, so just VC, over 2000. Now what we can do is find our common denominator so that we can get rid of our denominator. So that's pretty simple. That's going to be 12,000, and we get 4,000 times 12 minus VC plus 3,000 times VB minus VC equals 6,000 VC. And then from here, we can divide both sides of the equation by 1,000 so we don't have so many zeros. So we have 40 and then expand. So 48 minus 4 VC plus 3 VB minus 3 VC, and then that's going to be equal to 6 VC. And then we just have to simplify. So we have our 4 VC, 3 VC, so negative 7 VC minus another 6, so negative 13 VC plus 3 VB is equal to negative 48. So now we can multiply the whole side of the equation by both sides of the equation by negative 1. So I get 13 VC minus 3 VB equals 48. So this is our equation 1, and we can't fully solve this equation because we don't have a single linear equation. We need to find another linear equation and use substitution or elimination in order to find the value of VC and VB. So this is our equation 1. And for this equation, we analyzed node C. So I'm going to write that here. So now let's analyze node B. Oh, So for node B, let's take a look at our current direction. So node B, we only have one flow of current to node B and two flows of current out of node B. So our flow in is going to be VA minus VB over 2000, and that's going to be equal to, that's our current in, and that's going to be equal to, we have our current through resistor 3 and our current through resistor 2. So our current through resistor, our current through resistor 3 is going to be equal to VB minus VC over 4000 ohms plus our current through resistor 2, that's going to be VB minus VD over 3000. Now we substitute our known values, which is 12, and we know that VD is equal to 0. Now again, like the previous node, we're going to find our common denominator, which is 12,000. So we multiply both sides of the equation by that, and we get 4,000 times 12 minus VB equals, not 4,000, 6,000 equals 3,000 VB minus VC, and then plus 4,000 VB. And then once we get that, we're just going to expand. I'm going to divide both sides of the equation by 1,000 because we don't want to deal with all these zeros. So let's cross those out. And we get, I'm going to skip a few steps ahead just because this is all algebra. So we get 13,000 VB minus 3,000 VC equals 72,000. Oh yeah, we divided by 1,000. So we're going to rewrite that as 13 VB minus 3 VC equals 72. So this is our equation 2. And now if you'll notice, we actually have a set of simultaneous equations because both equations have the same two variables, and now we can use either substitution or elimination to solve. So what I found the easiest way for me to do it was elimination. So I multiplied equation 1 by 3, and I multiplied equation 2 by 13. So that gave me 39 VB minus 9 VC was equal to 216. And then 169 VC minus 39 VB was equal to 624. And now I just added both of the equations to solve for VC. And I got 160 VC is 840. So then VC is equal to 5.25 volts. Remember your units. So this is our first result. And now we can find our VB using this, and we find that VB will be equal to, if you go through the algebra, you will get VB equals to 6.75 volts. So now we officially have the voltage through each node in our circuit. So now it should be pretty simple to just find our potential differences between each node. So let's just go through that real quick. So the first question is asking, what is VA minus VB? And to find that, we just do 12 minus 6.75, and we get 5.25. For part B, we're going to do 6.75 minus 5.25, which would be our VB minus VC, and we get 1.50. Remember, units. And for part C, we're getting VA minus VC. We're going to do, VC minus VD, actually. So VC minus VD. So VC was, what, 6.7? Yeah, 5.25 minus 0, which is just 5.25. And part D was VA, which is 12, minus VC, which is 5.25. And that will be 6.75 volts. So these are our answers. So those were the solutions to our problem number 35 from Halliday Resnick Fundamentals of Physics. If you like more solved examples, you can comment them down below, and thank you.